is 2040, halfway between the Earth and the Sun. Here is an entirely new kind of telescope. Thousands of mirrors spread out in space send back their images to a central satellite. The goal is to observe the surface of distant planets. And here's the surprise. The image of a foreign world, hundreds of billions of kilometers from the Earth. Look at the blue and green spots. They're probably oceans and continents. And those glowing lines, could they be cities? Worlds of ice, worlds of fire, and giant planets, soon maybe a new planet Earth? How does life appear? Is it a rare or a common phenomenon in the universe? Billions of suns and billions of planets in our galaxy alone. How many inhabit intelligent life? If intelligent life exists in the universe, can we communicate, and what would we say? If intelligent life exists, why do they remain silent? What if we are alone, absolutely alone in the universe? Hundreds of planets, and soon thousands more to be discovered. We now know that the universe is filled with them. On some of them, there may be life, and perhaps even intelligent life. This is the new dream for the astronomers.
1, 5, 0, 0, 0, 0, many zeros to make the number of Earth-like planets, a huge number of Earths within our universe.
Now, to think that this is the only planet where there's something intelligent, that would be an incredible miracle.
We find that there are 31,513 intelligent civilizations in a galaxy of 1 billion stars.
Personally, I am ready to bet that in a century, we will discover life elsewhere in the universe.
This fascinating quest for new worlds started 50 years ago by exploring our solar system. However fascinating it was for astronomers, it disappointed those expecting to find life. But this exploration is not over, far from it, and there is new hope being placed in missions to the giant planets like Saturn and Jupiter. 2029 will be the year of our return to Titan, Saturn's largest satellite. Remember January 14th, 2005? The little Huygens probe showed us an amazing landscape of mountains and valleys, similar to a seashore. Blocks of frozen water could be seen on the ground under an orange sky. It was a strange world, so close, and yet so far from ours. 24 years later, in 2030, a new unmanned mission will drop 2 new objects on Titan, a 600-kilo hot air balloon and a small probe. Athena Kustanis, responsible for this US-Europe joint venture, tells us about this fantastic journey as if she was already there.
In this twilight, the balloon will move at 10 kilometers of altitude. And here, it's 200 degrees Celsius. It's very, very cold. So the cameras and all the equipment on board, cameras, analyzers, and all the rest, will take images of the ground. But we'll also use a few flashes to see what's at the bottom and what's around us. When we go through the atmosphere, we'll suck up the aerosols and see how this surface is built and what its organic chemistry is made of, which will allow us to understand the level of complexity of the organic chemistry and if it has the level that we have on Earth, which is necessary to make macromolecules and create life. At the same time, this balloon is moving in a very cold and very dark world.
Sent to one of Titan's hydrocarbon lakes, the little probe will look for the traces of a basic chemistry which reveals the presence of life.
The probe lands, and instruments will take samples of the liquid in this lake. We taste it, and with all the equipment on board, we'll make an analysis which will tell us, on the one hand, what this atmosphere is made of, and on the other hand, if there's liquid inside. To have liquid inside Titan, you need ammonia. This lander is showing us that, yes, there are traces of ammonia in this lake. Then we realized that there's an ocean inside of Titan, an ocean made of water, which may shelter life, if not today, then maybe one day.
We also expect to find life on Enceladus, another one of Saturn's satellites. Look at the horizon. Giant geysers of ice erupt at the surface. An underground ocean fuels them. The opportunity is too enticing. We'll also go to Enceladus.
Our orbiter gets close and dives into one of these geysers. It picks up matter, which we will then analyze on Earth.
Considering how cold it is on Enceladus and on Titan, the only kind of life that we might find would be a very basic form of life. It would be the basis of life rather than life itself. To find more complex forms of life, our hopes now turn to exoplanets, meaning planets that orbit around other suns. Today, a new satellite is in charge of finding distant worlds, and its name is Corot. We're in Toulouse, inside the National Center for Outer Space Studies. This is the team in charge of Corot. For the past 3 years, the list made by this planet-hunting satellite keeps growing.
This is the last one we found, Corot 9b. It rotates slowly around its star. It's a gas planet. It's far enough from its star to have a moderate or temperate climate, similar to the temperature we have on Earth. Unfortunately, it's a gas planet, so there probably isn't any life on it.
How can one find objects that small and so far away? It isn't enough to make the telescopes more powerful.
This is a small model that shows the rotation of a planet around its star. When the planet goes in front of the star, the light coming out of the star will lower slightly. Corot is so sensitive that it can notice when the light coming out of stars lowers slightly. Therefore, it can pick up on the signs that show that there are planets around these stars. The star is also slightly attracted to the planet and moves a little. This movement is detected by instruments attached to big telescopes on the ground. This second technique is used to confirm the existence of planets around other stars.
In the beginning, the planets that we discovered were inevitably large gas planets, not suited for life. As the years have gone by, we've been able to narrow it down. Astronomers are now discovering small rocky planets like the Earth. To reach the final goal, discovering a planet similar to the Earth, we will have to wait for a new generation of telescopes, hypertelescopes.
What is a hypertelescope? It is a set of small telescopes spread out on a surface, each of which act like a big, single telescope. Each of these small telescopes send the light they receive to a central telescope which combines everything it received from the little telescopes.
If you want to observe a whole planet, you need 20,000 square meters of mirrors. To observe its continents, you need 80,000 square meters of mirrors. And to discover any possible signs of life, you would need 500,000 square meters of mirrors.
If, for example, you want to see an image of the Bay of Saint-Malo, seen from a nearby star, seen from 500 meters away from the bay, you would need to set your telescope 300,000 meters away, the distance between the Earth and the Moon, and you would need approximately a 5 million square meter surface, which is about 1,000 times the size of a soccer field.
Tuesday, April 6, 2010, Academy of Sciences at Paris. On that date, Swiss astronomer Michel Mayor was giving a presentation in front of his peers about the search for planets similar to the Earth.
We can see those rings, that structure which gives us information about the existence of planetary systems.
In 1995, Michel Mayor was the very first astronomer to discover the first exoplanet, 40 light years away from the Earth. Here it is, 51 Pegasus, a giant made of gas, like our Jupiter. But the surprise was that its orbit was very close to its star. Michel Mayor is still excited about it today.
It's completely unusual. A planet that has the same mass as Jupiter orbiting very, very close to its star, going around in 4 days. Our concepts about the structure of big planets would not allow us to understand this. We had to reconsider the theory entirely to explain how this planet, which had to be very far away, evolved to get closer to its star. Currently, the entire theory about the formation of planetary systems has to include this.
A surprise right from the first discovery. Other discoveries will be on the same level. In the past 15 years, more than 400 planets have been discovered, each more amazing than the others.
The vast majority of planets that were discovered were our close neighbors. These are planets that are 10 to 100 light years away, which is already pretty far. But one experiment has been done to find planets that are even farther away. Basically, we took successive pictures for months of regions at the center of the galaxy. It was the OGLE experiment, OGLE.
Let's get closer to this small planet, which at first sight isn't much. OGLE 05390. Let's go to the surface of its frozen ground. We will have a surprise.
It's a frozen planet. It's very far from its star and very cold. Unfortunately, there probably is not any life on a planet like that, but the sky must be absolutely stunning. Why? In the central regions of the galaxy, the density of stars is much greater, about 1 million times greater than it is around us. So let's imagine the view of the sky one must have from a planet like this. A myriad of stars, 100 times, 1,000 times denser than what we have here. Unfortunately, we won't be able to go there.
Of course, astronomers are looking for a new Earth, but where can it be found?
We would like a little planet somewhat like the Earth, which is at the right distance so that it is neither too hot nor too cold. Gliese 581d is the first small place that finds itself in that situation. It still isn't exactly a planet like the Earth. Its mass is 7 times greater than the Earth. It's a bit too heavy, but it's at an inhabitable distance from its star.
Today, Michel Mayor has a very personal hypothesis about Gliese 581d. An ocean planet. According to Michel Mayor, it was once a frozen planet, which migrated and melted as it got closer to its star. The result is a huge ocean.
This has nothing to do with the extremely thin ocean we have on Earth, but an ocean that is maybe 100 kilometers deep.
Now here is an incredible object, PSR 1257+12, which has a fantastic story. This little planet orbits around a pulsar, the corpse of a star which spins and sends out a very intense jet of X-rays and ultraviolet rays. It was detected by chance in 1990 by a Polish astronomer, 5 years before Michel Mayor's official discovery. At that time, astronomers weren't sure if it was a real planet. We were wrong. It was the first exoplanet discovered. Corot's team has just found the smallest planet we know to this day, Corot 7b. It's barely bigger than the Earth. It goes around its star in less than 24 hours.
In other words, if Corot 7b had any inhabitants, the year would not even last a day. Sounds like the story of the Little Prince. Since it turns in less than a day, it's very, very close to its star. Very close to fire, so it's very, very warm. But since it always faces its star from the same side, just like the moon does with the Earth, it's very warm on one side and probably very cold on the other. So if you want to go from one side to the other, you would have to go from a bathing suit to a ski suit.
In 15 years, our perception of the universe has completely changed. Now it's full of planets. We went to Berkeley University, where we met one of the most famous American astronomers, Geoffrey Marcy. Along with Michel Mayor, he was one of the pioneers of the discovery of exoplanets. He did a little calculation for us at the cafeteria.
So we can estimate how many Earth-like planets there are in our entire universe in the following way. We know that there are 200 billion stars within our Milky Way galaxy, 200 billion stars. And we know that about 15% of those stars have planets. So if you multiply those two numbers together, you see that there are 30 billion planetary systems within our Milky Way. 30 billion planetary systems is a huge number of planets. But we might ask how many of them have Earths? And probably something like 50% of them have Earths. And so if you multiply 50% by 30 billion, you see that there are about 15 billion planets like the Earth within our Milky Way galaxy. 15 billion Earths, but that's just within our Milky Way galaxy. Now if you consider the whole universe, it has something like 100 billion galaxies like our own Milky Way galaxy. And so if you multiply these two numbers together, 15 billion Earths within each of 100 billion galaxies, now you see when you multiply them you get 1, 5, 0, 0, 0, 0, many, many zeros, 24 zeros. A huge number of habitable planets within our universe.
We've gone beyond the realm of astronomy. We're going through a huge philosophical revolution, which completely changes the consciousness that man has of his place in the universe. Now, let's take time to contemplate our Earth. Thick jungles, waterfalls, lakes, oceans. These landscapes don't seem to exist often in the universe. So far, most distant worlds that have been detected by astronomers are most likely frozen or burning deserts, therefore barren. In contrast, the Earth is full of life. In the savanna, in the forests, in the depths of the ocean, in deep caves, and in our cities with millions of intelligent beings. How is this exception explained?
Personally, I am very comfortable with the idea that life is a natural byproduct of the evolution of the universe. When the conditions are put together, life has to develop. That does not mean man, that does not mean a form of life similar to ours. What is more probable is unicellular. That is probably the most widespread form of life that exists. Personally, I am ready to bet that in a century, we will discover life elsewhere in the universe.
Let it be known that Michel Mayor's optimism isn't just a belief. It's confirmed by very objective research which takes place in laboratories all over the world. We're in the French Society of Exobiology. These aren't fans of science fiction, but biologists, chemists, astrophysicists, who are experimenting on forms that life may take on planets other than the Earth. In this laboratory, exobiologists have recreated the atmosphere of Titan, Saturn's big moon. The mixture in this test tube is made of nitrogen, methane, and carbon monoxide. Then it's dipped into liquid nitrogen at minus 170 degrees, which is the temperature on Titan. Finally, we circulate an electric current between two electrodes, which simulates the ultraviolet rays of the sun. We let it rest a few days. And look at the result. Those blackish compounds which are made of carbon and hydrogen. They are organic compounds, the bricks that are at the base of life. In 1953, an American biologist, Stanley Miller, did a similar experiment by reconstructing what he thought was primitive Earth's atmosphere. Methane, ammonia, hydrogen, water vapor. And he also obtained organic compounds. To the public, this discovery struck like a lightning bolt.
The public did not realize that it was that easy to obtain biological compounds. In experimental situations which are really quite simple, the fact that it was easy was a huge surprise. A huge surprise to the public and a huge surprise to certain scientists, who did not think that in such a short amount of time, one could construct the elements at the basis of life.
Let's not be too hasty. It's one thing to have the bricks, but you still have to build the house. For over half a century, we know that the blueprint is inside this long molecule called DNA, deoxyribonucleic acid. Alas, you can't find it at the bottom of a test tube.
In these experiments, we obviously don't build bacteria, microorganisms. Neither do we build nucleic acids or even proteins. What we build are the bricks of these giant molecules. Amino acids are the elements, the bricks, that form proteins. We also build small pieces of nucleic acids, but small pieces, really small bricks. To go from these small pieces to the macromolecule is like going from a few bricks, a few stones, to a cathedral. And it does not happen overnight.
To understand how everything started, we must go on a long journey, 4 billion years ago, into the inferno that was primitive Earth. Asteroid showers, volcanoes spewing their lava, a boiling ocean, a suffocating atmosphere, 100,000 times richer in carbon dioxide than ours. In 2008, in an animated film, Voluntarily Naive, researchers from the CNRS had fun by popularizing what we know about the very first moments of life. They chose to tell us about the adventures of a small water molecule, Picolina. After arriving on Earth aboard a comet, Picolina is going to witness the birth of life inside the primitive oceans. At first, she sees isolated and simple molecules, like methane or carbon dioxide. Then more complex molecules, like amino acids, Stanley Miller's famous bricks. But one day, Picolina meets something astonishing.
One day, I stumbled upon a kind of huge molecular snake, a polymer. Dozens of molecules were attached to each other in single file. What a strange idea! I met others, more and more, which seemed to come out of a crack at the bottom of the pool I fell in. I wanted to be sure. I got closer, and here, how spectacular! Molecules from the same family attached to clay crystals were arranging themselves one next to the other.
Actually, this little trip that she's telling us about shows the complexities of matter. We go from little molecules with carbon. Most of them have carbon atoms in their structure. And those molecules are able to become more complex, to react to one another, to become bigger and bigger. It keeps getting bigger and bigger, becomes giant molecules, what chemists call macromolecules. And some of these macromolecules will be able to multiply, to make copies of themselves. Once these big molecules that can copy themselves have appeared, that's the beginning of life. We can say that these macromolecules that can make copies of themselves are the first living organisms.
It may be like this that life appeared on other planets, turning around other stars. To light the spark, a few simple conditions are enough.
If we consider what happened on Earth, which is still the reference in this field, there seems to be 3 essential elements, which are carbonated matter, liquid water, and energy sources. And when we go to find life elsewhere, in the solar system to begin with, we will be interested in environments where these 3 conditions, these 3 ingredients are present.
If these 3 conditions are present, then everything is possible. On our planet, we can find life in the most extreme places.
For example, we are discovering life in the depths of the ocean under powerful pressures, living organisms called barophiles. Barophile meaning who loves high pressures. In lakes where the level of salt is very high, the Dead Sea, for example, where the level of salt is at the maximum, we have found something we didn't expect. We found lots of organisms called halophiles. The most extraordinary organisms are, without a doubt, hyperthermophiles, which love very high temperatures. So far, the record is 121 degrees Celsius.
Let's stop here. We now know the rules in the game of life. And we can see on our Earth alone a whole spread of possibilities. But on distant worlds, that spread can still get bigger until it can compete with science fiction's wildest creations. Now let's go further. This is the Seattle Space Needle in the state of Washington, the landmark that represents the city the most. In the University of Washington, we discover an amazing laboratory, the Virtual Planet Laboratory. Here, exobiologists create virtual worlds, which will help astronomers get a better understanding of what they find in their telescopes. Recently, they asked themselves a very simple question. What could be the color of the vegetation on worlds orbiting distant suns? Green? Not necessarily.
So on our planet, the foliage is green, because that is the color of light that plants don't really utilize on our planet. So they reflect that light backwards, and we get green light reflected to our eyes or to the camera. On a planet with lots of light coming to it from a very hot star, you might have too much blue light, and so they'd reflect that blue light because they don't want to use it. And then that light would get reflected to our eyes or to a telescope, and so the planets would appear blue. And on the sides, we have the color black. And the color black is the presence of absorbance of all color. Nothing's getting reflected backwards. And so a planet which has not much light coming to it from its parent star, if the star is cold and doesn't give off many photons, you might want to absorb and get your hands on all the photons possible and absorb all the photons you can. And if you do that, you're not going to reflect anything. And then the color that that planet would have would be black. And so the color of leaves on some planets may be black.
These simulations can be extended to life forms that are adapted to conditions that are very different from ours. For example, a giant planet where gravity would be much stronger than on Earth.
If a planet had a lot more gravity, it might hold onto its atmosphere. And on Earth's atmosphere, we've lost hydrogen through the top of the atmosphere through time. That's left behind oxygen and ozone. If that didn't happen because the planet were larger and heavier, you might end up with no oxygen and no ozone. And then the plants or the organisms on that planet would need to shield themselves from ultraviolet light. And one way they do that is by living in oceans. Another way is they form matted communities that end up looking quite a bit like rocks, except they're actually mats of organisms, layers of organisms, like these organisms here called stromatolite.
Of course, what we're interested in is intelligent life. On which planet would we have a chance of discovering it?
Well, we have a good image of what an intelligent planet looks like. Earth. And we hope to find Earths this decade. This is going to be the most important scientific discovery we're going to make in the next few years. And once we find those planets, we're going to want to know if they're alive. And that's where we come in.
According to another exobiologist, Michel Vizot, this type of experiment has its limits. All you have to do is imagine the experiment the other way around.
Let's imagine extraterrestrials who have observed the Earth. They see that there is land, seas, plants, air. They're going to imagine life forms, or a form of life adapted to these conditions in their logic. If by chance they arrive, they're going to find a complete abundance of life. Plants, animals, bacteria. They're going to find elephants, giraffes, flies, birds. Life forms that are extremely different and share the same biotope, the same small unit. So we quickly realize that it is a bit vain to assume what form life may take, simply based on physical and chemical information that we can observe on a planet. If one day we have the chance to find an extraterrestrial life form, if we get the chance to meet it, firstly, it won't be alone, and secondly, we are going to be surprised.
Life, yes, probably. But what about intelligent life? In 1961, a famous radio astronomer, Frank Drake, suggested an equation to try to estimate the potential number of extraterrestrial civilizations in our galaxy. And this is what it looks like. Don't be afraid. It's a very simple equation. Combining the number of planets where life appeared, the number of planets where it evolved towards intelligence, the number of civilizations that can communicate. For pessimists, the result is only one. Only one civilization, ours. But for optimists, there should be several thousands. The optimistic tendency, we find it today in the beautiful city of Edinburgh in Scotland. In the library of the Royal Observatory, we met a young researcher, Duncan Forgan, who surprised the scientific world by estimating the probable number of intelligent civilizations in our galaxy. To achieve this calculation, Duncan Forgan was given access to the university's supercalculator, which worked for 12 days, or a bit over 200 hours, on 3 possible scenarios.
In the first scenario, we put in information that life is difficult to form. So this is a hypothesis. And we say that if life is difficult to form, but it doesn't manage to form on a planet, it can evolve into an intelligent civilization. And we find that in our models, if we put this information in, there are 361 planets with intelligent civilizations in a galaxy of 1 billion stars. In the second scenario, we're more optimistic about life, and we assume that it can form in more places than in the previous scenario. However, the civilizations that arise from those life forms have an extra sociological pressure placed upon them. Basically, that the longer it takes them to evolve from a state where they may be vulnerable to a state where they become stable and advanced, the longer that time period takes, the more likely they are to destroy themselves using their own technology. And in that scenario, we find that there are 31,513 intelligent civilizations in a galaxy of 1 billion stars.
The last scenario relies on a scattering of life in the galaxy through comets and asteroids. The result? 37,964 intelligent life forms.
But of course, where are they? And the problem seems to lie in the fact that while 2 civilizations may arise in similar points in space, they may not arise in similar points in time, and you need to meet both those criteria if you expect 2 civilizations to contact each other.
Let's say that some of these civilizations live in the same period as us. What could they look like? In 1964, Russian astronomer Nikolai Kardachev suggested a theory to classify them according to how much energy they consumed. First, there are Type 1 civilizations. They survive by using all of their planet's energy. But we're still very far away from it. We will probably have to wait several centuries to become a real Type 1 civilization. Type 2 civilizations are a lot more advanced. They use all of the energy coming from their star. And this is how we could imagine them. A giant set of rings, 1 billion kilometers in diameter, built around a sun that could be similar to ours. This fantastic ring allows the super civilization to collect all the energy of its star. Around 100,000 billion kilowatts for a star identical to our sun. Inside those structures, millions of populations live in homes built according to their will. Of course, Type 2 civilizations are millions of years ahead of us. They probably already master interstellar travel and technologies which we don't have the slightest clue about. Finally, there are Type 3 civilizations. They use all of the energy in their galaxy. They should be between 1 and several billions of years ahead of us. Yes, but once again, where are they? Normally, such civilizations should send out radio signals that we could pick up. Thanks to our radio telescopes, this is the goal of the famous SETI project, or Search for Extraterrestrial Intelligence. The problem is that until now, the sky remains silent. We're in San Francisco. We immediately head south towards the little town of Mountain View, where the headquarters of the SETI Association is located. Here, the skies are tirelessly examined to find a radio signal, an intelligent signal sent out by an extraterrestrial civilization. Yes, but it's been 50 years and still nothing. How can we understand this silence?
My mother even occasionally will call me up and say, you know, are you doing the job you really want to do? Well, I am. And the reason is we haven't found a signal yet, but the experiment is getting faster. It doubles in speed every 18 months. And so that means that whatever we do in the next 2 years is more collection of data than the past 50 years put together. So that's what keeps me going. The thought that, yeah, we haven't found anything so far, but in the next 20 years, I think we will.
Mr. Shostak, I have a surprise for you. It comes from Nancy, the radio telescope of Nancy.
Okay, all right. Well.
It was definitely a surprise. This message was received a few days earlier by the radio telescope of Nancy in Sologne, France. Although it's mainly used to explore the sky, this powerful radio telescope is sometimes used to pick up possible intelligent radio signals. And this is what attracted the researchers' attention.
This is the spectrum of the radio waves we receive with the Nancy radio telescope. This peak here is the intelligent signal we can expect from an alien civilization. It is extremely thin. Here it varies, then disappears. It is the presence and the absence of this signal that can indicate a code. Here it is again. We can imagine that it's a binary code, a series of ones and zeros, which we have to decode.
This is the binary code, a series of ones and zeros, which obeys to a hidden logic.
If we count the numbers, we get 583, and 583 is equal to 11 times 53. So we organize these numbers, and this is what we get. 53 lines and 11 columns, and we get a little drawing.
To understand the following, we have to go 36 years back. In 1974, with the powerful Arecibo radio telescope in Puerto Rico, astronomers sent into outer space this message to the stars, containing information about us Earthlings. Numbers from 1 to 10. The atomic numbers of a few atoms, and even a sketch of a human being and his size and other details. So now we could guess that this message was picked up by intelligent beings who sent it back to us slightly modified.
So here we find what we sent to Arecibo. We have the numbers 1, 2, 3, 4, 5, 6. So maybe it was sent by someone who counts by 6, and for example, who has 6 fingers. Here we maybe have a star and planets around it. There are 6 planets, and we notice that the 4th is set aside, so they're probably on the 4th planet. This is what they could look like. And this is probably the radio telescope which allowed them to pick up or send out this message.
At this point, what do we do? How is the news announced to the world? The SETI Association has thought about this question a long time ago. They established a very precise protocol.
If you receive this message at the Nancy telescope, you may think the first person to be told is President Sarkozy, the president of France. If the Americans pick up a signal, why not talk to the president? But according to the SETI protocols, these messages that we get from extraterrestrials are not aimed at any particular country. They are being sent to Earth as a whole, and so they are the property of Earth as a whole.
Well, the protocol, if we pick up a signal, is very simple. The first thing you do is you verify that it's truly a signal from ET, because you don't want to mislead people. The second thing is you would tell every astronomer in the world, hey, there's a signal coming from this spot on the sky, because you'd want them to study it day and night. Then you would tell everybody else, and of course everybody else would already know, and that includes the media and of course the public and the governments and so forth.
If we want to answer to this message, one thing is clear. The extraterrestrials are very interested in the human form, or in their form, and they're telling us that's something that we have in common. So we might send something very similar to this. Start with the same picture of the human form in the Arecibo message, and now we want to show that we have parts to our body. So let's focus in on this arm. We have arms, and those arms can move. Now we return back to the entire human body. We can also have a close-up. We focus in on one part at the end of our arm, what we call our hand. Now notice here, we have 5 fingers. Or we might want to say something about what our faces look like. And so here's the human face, and we focus in too on our eye, that important sensory organ for us. So we show a picture of the eye, and it's not just this static eye, but an eye that can close, either very slowly, or we can show it in contrast and show it closing quickly. But ultimately, I think what we would want to say is we got their message, and now in return we send a greeting back to them.
Of course, sadly, this was only a simulation. Once again, we haven't received anything for now. So here's the question. What if we were alone, absolutely alone in the universe?
The number of planets in our own galaxy is probably a million million. A million million, and most of those planets are probably not very interesting, but some of them are going to be good. And if you don't like our galaxy, hey, there are 100,000 million other galaxies, each with a million million planets. Now to think that this is the only planet where there's something intelligent, that would be an incredible miracle. And one thing you learn after being a scientist for a while is you don't believe in miracles.
On the side of the pessimists who don't believe in miracles, we find biologist Peter Ward, author of a groundbreaking book, Rare Earth. According to him, life is abundant in the universe, but intelligence is rare, maybe even unique. Apparently, we are alone, but not forever.
Maybe it's not so much that we are alone, but that we're the first. Maybe we're the first intelligence to arrive at a technical ability. And maybe it is our fate not just to be the first, but to be the seed of moving humanity to another planet where human beings become something else, or another planet, or even a different galaxy. So that would be a much more optimistic, that's not pessimistic, it's wonderful.
Now, more than ever, we have to remember that the scale of the universe is different from ours. We have to remain patient in the face of this immensity. We have to wait. How long? No one knows. But for some, we will get an answer one day. And that day, everything will change for humanity.